Okay, here's part 3 of your notes. This symbol that you see here is what you're going to see on your periodic table. And what you need to remember again is this is number of protons. Okay. This is the element symbol. And this is the atomic mass. Atomic mass. And what is the atomic mass? Atomic mass is simply the number of protons and neutrons in an atom. Okay? It's the number of protons and neutrons in an atom. So why is this why are there these decimal places after the atomic mass? Well, that's because there's different isotopes of this element. Okay, that not all of them have exactly 6 protons and 6 neutrons in the nucleus. There might be a very, very small fraction that has 7 neutrons in the nucleus. Okay, so scientists take the average of all of these isotopes and add them up, and then they calculate the atomic mass based on that. And that brings us to this second part, which is called isotopic or isotopic notation. So on the periodic table, you'll see the notation like this. It's very easy to confuse isotopic notation with this periodic table notation. Okay, I'll call it the classical notation. And isotopic notation, these two numbers are actually reversed. So you'll have to use your periodic table to decipher this. But in isotopic notation, these two numbers are reversed. So you end up with number of protons, that's atomic number. And let's go ahead up here and do the same thing. Number of protons, that's also atomic number. That's the atomic number. Okay, and then this is number of protons plus neutrons. That's what this number is right there. That's the number of protons plus neutrons. We call that the mass number, or the mass number is a better way to say it. Okay, so number of protons. Sometimes we say atomic number too. I'm sorry, atomic mass as well. Atomic number in this case is going to be number of protons. And that's going to be 6. And our mass number is going to be 13. Okay, that's our mass number of 13. So in example 1, state the number of protons, neutrons, and electrons in Cl minus. Okay, so let's go ahead and do that. Number of protons. It's going to be 17. Number of neutrons. Well, I'm going to take 35 because that's the number of protons and neutrons, and subtract 17. (35 minus 17), and that's going to give me 18. 18. Okay, because again, that mass number represents the number of protons and neutrons. Okay, and excuse me while I change the camera around here. The number of electrons, well, this is not a neutral atom, is it? Because we have that right there. That tells us there's an extra electron. Okay, in a neutral atom, there's going to be the same number of electrons as there are the same number of protons. But that's not the case here. We have an ion. This charge right here just tells us we have one additional electron, rather. So if a neutral atom had 17 electrons, this is going to be 17 plus 1, which is 18 electrons. 18 electrons. Okay, let's go ahead and do an example number 2. Mass number 60, atomic number 26. Okay, so the first thing you need to do is you look at the atomic number. When you're given a problem like this, you look at the atomic number, which is 26. That's iron. So you start out by writing Fe. I'm going to write the atomic number down here, 26. I'm going to write the mass number 60 up there. It's got a charge of +2. +2. All right, so let's go ahead and figure all of this out. So number of protons. Number of neutrons. Remember, that's protons plus neutrons. That's going to be 60 minus 26 for a grand total of 34 neutrons. And the charge of +2. Okay, so it's got a +2 charge. Remember, it's missing electrons. Don't forget that now. Right? If you've got a plus charge, you're missing electrons. Look, 1, 2, 3 protons, 2 electrons. You got +3 minus 2, or +3 plus a -2, right? So that gives you a +1 charge. In this case, you've got a +2 charge. So how many electrons am I missing? I'm missing 2 electrons. So 26 minus 2 electrons for a grand total of 24 electrons. Okay, 24 electrons. Okay, so this last problem, example 3, answers the question, why do we have a decimal point after these atomic masses here? Why is it not just 6 protons and then atomic mass of 12, 6 protons and 6 neutrons? Okay, and the reason why is this. In nature, there are isotopes, and sometimes carbon might have, most of the time it's going to have 6 protons, okay, and 6 neutrons, but on occasion it might have 7 neutrons and 6 protons. So let's look at this problem. 99% of carbon atoms are carbon-12, and 1% of carbon atoms are carbon-13. Assuming the mass of each isotope is its mass number, calculate the atomic mass of carbon. So here's how you do this. Imagine we have, I'm going to write something here, and you guys can copy that. Okay, I'm going to write something here. I'll read it, and then I'll put it up on the screen for you. Imagine that we have 100 carbon atoms. 99 of them weigh 12 AMUs, and 1 weighs 13 AMUs. The average would be calculated this way. Okay, so here's how you do that. Okay, 99 C12 okay, 99% of the atoms are carbon-12 times their AMU, which is going to be 12 AMUs, plus one of those atoms is going to be carbon-13. And its AMU is going to be 1. Okay, 1 AMU. So out of that sample, 99 of them were C12, and only 1 of them was C13. Okay, out of that sample, we're going to take the whole thing and divide by 100 atoms total. Okay, so of our sample of 100 atoms, 99 of them were carbon-12, and 1 of them was a carbon-13. One of them was a carbon-13, and that should be 13 AMUs, not 1. 13 AMUs. Okay, you had 100 atoms. 99 of them were carbon-12, 12 AMUs, one of them was a carbon-13, and 13 AMUs divided by 100 atoms total. When you do that math, you get 12.01. And if you look up here, that's the atomic mass of carbon, okay, equals 12.01. So that's how you calculate those problems. That's how you calculate the atomic mass based on different isotopes. And that concludes our notes.